pleasure to introduce Dr. Hart, who will be beginning his PhD thesis today. Titled Self-Healing of Impact Damage and Vascular Fiber-Reinforced Composites. He's been with us for a few years now. Came to us from Urbana, University of Wisconsin, where he made a name for himself, not only in the undergraduate research lab of a colleague Wendy Brown, why he got hired, but also on the football field with the band. He's a die-hard Badger, but we've turned him into a fighting Illini. We haven't signed it.
Go Illini!
All right, so the way this will work is Kevin will present his work here. We'll simply entertain questions from the audience at any moment. Just raise your hand or say, Kevin, I don't understand. We certainly will. And then at some point, we'll take some general questions. And after that, we'll ask those who want and leave. We'll reconvene with just the committee and whoever's interested to question, give us a little bit more intimately, shall we say, about the work. But it may take some while to get prepared. Okay, any questions? All right, Kevin, take it away.
Okay. Thank you everyone for coming. It's nice to have a really big audience for my presentation today. I'm going to be presenting my dissertation work with the same title as my presentation today, which is Self-Healing of Impact Damage and Vascular Fiber-Reinforced Composites. So an outline of the talk today, I'm going to go through an introduction quickly on impact damage and fiber-reinforced composites. I'm going to talk about my contributions, looking at impact damage characterization, and also things that I did to accomplish self-healing from a few different types of specimens, including double cantilever beam specimens and impact specimens. Then I'll conclude, I'll provide a summary of my contributions, and finish with the acknowledgments. So, first the introduction. I think many people in this room are familiar with fiber-reinforced composite materials, but fiber-reinforced composites are structural materials with two or more chemically distinct phases. These two different phases are usually visually observable in a cross-section. And for my particular work, the reinforcement phase I'm going to focus on is glass fiber, and the continuous matrix phase is an epoxy polymer. And so we're going to look at a lot of these cross-sections like something like this today. I just want to highlight a couple of key things in these, including the toes of glass fibers going across the plane here, some of them coming out of the plane at us, as well as epoxy regions here. So you see the chemically distinguishable components here. And composites are beginning to emerge in our world at a very fast rate. And so they're useful in applications demanding very light, very strong materials because they have excellent specific strength and stiffness in the wave ratios. And so they emerge in fields like the automotive field, the aerospace field, and wind energy, where both mass conservation and stiffness and strength are required. So to give you an idea of how fast these materials are growing, in 2015, the carbon fiber composite world market was valued at $16.5 billion a year, and that's expected to double by 2019. So that's a tremendous growth rate for these particular materials. But they're not without their disadvantages. And one of the disadvantages of composite materials is they're typically made with a brittle matrix phase. And that brittle matrix phase leaves them susceptible to out-of-plane impact damage and can cause damage inside of the material that is large scale and complex. It can compromise the structural integrity of the part. And so here we're just showing a cross-section of a composite with a couple of different damage types. Here we see delamination between fabric layers, shear cracks occurring, and in some severe cases of impact we have fiber failure. Fortunately, I was lucky enough to join a group that worked with self-healing polymers, and the original idea behind self-healing polymers was we wanted a material that had the ability to heal itself when damage was introduced automatically without human intervention. And that first demonstration was done in 2001 with a capsule-based system. So in this schematic here, we have a microcapsule embedded inside of a polymer system, and this microcapsule has hard outer shell, liquid core on the inside. And as the material is damaged and crack propagates through, the liquid is released and reacts with some sort of catalyst or some other chemical inside of the crack to heal the material back together. So if we consider the damage that actually occurs inside of a composite, it can range in size scale from roughly 1 micron in the case of tensile cracks, for instance, seen here, up to hundreds of microns if we have fabric separation, or what we call delaminations. And if we consider using a capsule-based approach for healing these types of damage, it's good for healing the low ends, so things like 1 or up to 10 microns roughly, but once we have very large damage separations like those of delamination, which we have during impact, the crack separations become so large that the microcapsules just don't have sufficient volume to fill all of that damage. So this was demonstrated by work by Yves Patel, who is in the audience today, which is awesome. And in his work, what he did was created 2D composite plates with microcapsules between the fabric layers and impacted them on a plane. So what he showed that composites containing self-healing components had compressive residual strengths higher than those of the control case at low impact energies. But at higher impact energies, the self-healing composites converged to the control case. And the reason for that is at low impact energies, the damage separation was small enough that we had enough volume of healing agent to fill the damage. However, at higher impact energies, the crack separations were too large and the capsules could not fill the damage. Fortunately, there are a variety of different techniques for self-healing polymers and materials, and the capsule-based system is only one of these techniques. And so what I showed in the previous slide is a demonstration of sort of the limitation of capsule-based systems. But fortunately, there's a few other different types, including the vascular-based system and intrinsic-based system. And so vascular-based systems differentiate themselves from capsule-based systems as they have internal vasculature which holds the healing agents as opposed to discrete capsules. And the intrinsic-based systems are use sort of a molecular bonding inside of the material to heal across the crack face. So intrinsic-based materials suffer from the same problems as microcapsule-based materials, and intrinsic-based materials require molecular bonding across an interface and thus require very small crack separation. So they're not particularly useful for our situation. But vascular materials are useful. And the reason is you can have multiple healing agents or multiple deliveries of healing agents, and you can theoretically fill an infinite amount of damage, which is good for our situations where we have a large amount of impact damage present. So if we consider biology, I mean, there are many, many living materials in our world that have this biological vascular network embedded inside it. So we're taking some analogies from biology and applying them to our materials. And biological materials used as vascular materials are temperature regulation, self-repair, nutrient transport, toxin regulation, many, many different things. And so we want to take this biological analog and apply it to synthetic materials. And the way that we can do that is we can manufacture vasculature inside of our materials using what we call the vaporization of sacrificial components material, or method of manufacture. In that method of manufacture, we take advantage of what we call sacrificial fibers. And sacrificial fibers are sort of highlighted in pink here. What we can do is we can co-weave these sacrificial fibers with the glass fiber preform, then infiltrate the composite with resin, where it then becomes a hardened solidified composite with that sacrificial material embedded inside of it. Then we can raise the temperature of these composites to 200 degrees Celsius for 24 hours, where that sacrificial element then depolymerizes and evacuates from the system, leaving behind a series of hollow channels inside of the composite. Then we could fill the hollow channels inside of that composite with whatever functional fluid we desire to apply whatever multifunctionality we would like to demonstrate. And in the original publication, they did this in a variety of ways. So using the same composite, they had a heated composite that passed coolant through to keep the material cool. They did a chemical reaction inside of a composite. They changed the magnetic properties of the material using a ferrofluid, and they embedded a liquid metal inside of the material to change the electrical conductivity. So what I want to do is I want to introduce vascular networks for self-healing applications. And it will broadly follow a scheme that looks something like this. So if we have a composite laminate that has vascular networks running through it, these vascular networks are going to contain one of a two-part healing agent system. Then as the material is damaged and delaminations propagate, the materials spill into the crack plane where they mix, polymerize, and heal the material back together. So this is the basic scheme that I'm going to follow for my self-healing applications. So that sort of brings me to the objective of my PhD work over the last 5 or so years. One objective would be to characterize the damage formation and mechanical performance of these impacted composites. Because if we're going to attempt self-healing, we need to be intimately familiar with the damage that forms and what damage leads to reductions in mechanical performance after impact. Secondly, we're going to develop methods for healing impact damage using vascular delivery of these healing agents. Thirdly, we'd like to investigate some alternate chemistries for this vascular healing scheme. I'm not going to have a lot of time to talk about that today, but it was something that was important in my work. So, continuing on with my contributions now. we'll look at impact damage characterization and post-impact mechanical properties. So if we consider some of the factors that influence damage formation and propagation, we can largely classify them into two different sort of factors. One would be material factors, so that would be things like the matrix material toughness, fiber ductility, interface sizing selection, and hybridization. So like a thermoplastic matrix would be a thermoplastic coupled epoxy matrix would be a hybridization idea. We can also consider architectural factors, so things like do we have interleaves between fabric layers? What is our stacking sequence? How does that affect damage propagation? Do we have stitches or Z-pins moving through the material? And are we using woven architectures? And woven architectures were particularly interesting to me because there's sort of a hole in literature which I could fill during my impact damage study. And so for that reason, I investigated some of the differences between 2D and 3D architectural composites. So what I mean by these 2D and 3D composites is kind of the architecture of the glass fabric before it gets created. And so 2D composites that are typical can be an over-under weave or fibers going, let's say, in X direction here and Y direction here. Whereas a 3D fabric can have X direction in yellow, Y direction in green, and maybe a through thickness toe, which we call a Z toe, that provides reinforcement in the third direction, which is why we call it a 3D woven composites. So 3D composites are relatively new to the world of mechanical composites, and there was a review article done in 2010 where the author concluded at the end of that review article in a comparison between 2D and 3D composites. He said it is not possible to state conclusively that 3D composites are superior because many researchers failed to report important data, including the inclined fiber volume contents of 3D and equivalent 2D materials needed to interpret improvement properties. And so this is where I saw a hole in the literature and what I wanted to take advantage of. And so until now, there was no study comparing damage formation and post-impact properties of 2D and 3D woven composites made from the same materials. So the impact protocol that we employ to kind of look at the damage and evaluate the post-impact properties is the Fletcher-Esser impact protocol. In this protocol, we make beam specimens that look something like this, about 110 millimeters long, 20 millimeters wide. And we clamp those specimens in a fixed configuration and impact them out of plane with the cylindrical impact head. Then after we introduce impact damage, we can take those samples into a 4-point flexure to determine their flexural strength and stiffness. A little more detail about the impact protocol. We're using 25.4 millimeter radius of curvature impact head. The unplanned length here is 40 millimeters. We're using an impact energies ranging between 0 and 25 joules, and the impact velocity is roughly 2 meters per second. So this is considered a low velocity impact. We're recording the time, load, and velocity, and from that we can calculate displacement using simple 1D dynamics. Post-impact flexure testing. Here the inner span is the same as the unclamped region in the impact, so 40 millimeters. The outer span is 80 millimeters. We're measuring the flexural strength using Eulerian beam mechanics. Where here P is the load, L is the total span, W is the width, T is the thickness. And we're measuring the secant flexural modulus, E here, which is stress as a function of strain divided by the strain between strain values of 0.003 and 0.003. To fabricate the samples, we're again using the same epoxy matrix for both 2D and 3D architectures. We have a dibicylyl ether bisphenol F resin and an aromatic amine hardener, the EPON 862 Epicure W system. We're fabricating these using a vacuum-assisted resin transfer molding technique, or what we call BARTM, at 70 degrees Celsius in an oven. And we cure these samples for 8 hours at 121 C to solidify them. The 2D fabric architecture is comprised of 5 layers of 24 ounce per square yard S2 glass, giving us a total aerial density of 120 ounces per square yard. That yields a fiber volume fraction of roughly 52% and a thickness of about 3.1 millimeters. The 3D fabric, in a similar analog, has 1 layer of 120 ounces per square yard fabric. Again, it's an S2 glass and it's woven orthogonally, like you see in this picture here. And so it's important for us to match the materials, so the fiber type and the epoxy type, as well as the aerial densities of the fabrics to minimize the differences in the architecture as much as possible. These yielded fiber volume fractions of about 47%, had thicknesses of about 3.5 millimeters. We take a look at typical load versus time curves for increasing impact energies. We note that at the lowest impact energy that we tested, which is 5 joules, we had a typical elastic response during impact, which is just load and unloaded. However, as we increase the impact energy to 10 and 15 joules, for instance, we start to see these sudden discrete load jumps, which occur at roughly 2,500 newtons. And as we increase energy, we see these load drops occurring more frequently. And these load drops correspond to the introduction of a very particular type of damage inside of our composites, and that damage is lamination damage. So if we take a look at a cross-section of one of our beams after it's been impacted, and compare one at low impact energies versus one at higher impact energies, we compare a sample with 5 joules, for instance, here. This is the cross-section. This is the corresponding binary conversion of the damage. So we see the cross-section here, no damage present, or very minimal damage present, compared to the 10 joule case where we have this very long fabric delamination between 2 layers, which is, again, sort of amplified by this binary conversion image. So interestingly, when going through the literature, we can kind of see that other authors have identified this drop in the load during impact and have actually coined it the delamination threshold load. So the load requires to introduce delamination damage inside the specimen. So this is from another author's work where he's identified this first reduction in load as the delamination threshold load. And again, this corresponds roughly with what we see in our specimens. And so we can look and identify this delamination threshold load for both of the architectures across a variety of impact energies and plot that. So here we're plotting this delamination threshold load value as a function of impact energy. And what I found extremely interesting is this delamination threshold load is consistent across the impact energies and across architectures. And so what this tells us is that this damage initiation, so the initiation of the delamination damage, is really dominated by the materials and not by the architecture. So this is consistent with some of the other studies as well that have looked at these sorts of phenomena. Then we can take these damaged specimens and evaluate them in flexion. So if we look at typical stress strain curves for these samples, and we look at a variety of different impact energies imparted to those samples, we can see that as the impact energy increases, we start to see less and less stress failure, and also lower moduli during the flexion testing. If we plot the flexural strength as a function of impact energy across those different impact energies, we see that with the 0 and 5 joule cases, this residual strength of these composites is roughly the same. However, after this line isn't showing up very clearly here, there is a vertical line here. After we pass some sort of threshold energy to introduce the laminations, we start to see significant reductions in the flexural strength. And so it's really telling us that this delamination damage mode is driving the reductions in mechanical properties. What's also interesting to note here is that the 3D composites tend to retain significantly more flexural strength after impact damage has delivered when compared to 2D composites impacted at the same energy. So what we wanted to do is sort of characterize, well, our hypothesis was that 3D composites might have less damage because of that 3-thickness toe compared to the 2D composites, and that might be why the residual strengths are higher. So we looked at the delamination sizes of these samples after they had been impacted. And we looked at 2 different metrics. One metric is the delamination length, and so that's simply the total length of the delamination in these images. And we also looked at the delamination opening, which is the total cross-sectional area of the delamination crack opening in these images. So all the pixels summed together, multiplied by the calibration of the single pixel. So if we plot these delamination metrics as a function of impact energy, we see that as we increase the impact energy, the delamination size grows for both the length and the opening, which is rather intuitive. The more energy you deliver, the more damage you're going to have. Interestingly, and sort of expectedly, the 2D composites tend to exhibit more delamination opening and length as we increase impact energy compared to the 3D composites. And we believe there's 2 mechanisms which kind of act to limit the delamination opening in the 3D composites. Those mechanisms are sort of depicted, one of the mechanisms is depicted in this image. So in this image we have a cross-section of a composite with a through-thickness toe running through our 3D weave. So this is our Z toe again. And one of the mechanisms that limits the delamination is what we call delamination deflection. So as these delaminations grow, they eventually have to run into this through-thickness toe if they want to propagate any further. However, this deflection downwards or upwards, which occurs at the Z toe, requires energy. And that energy is not going into creating more free surfaces now, it's actually going towards deflecting the delamination downwards or upwards. So that's one mechanism that limits the delamination opening. And the other is simply the through-thickness reinforcement that the Z toe provides, the sort of a restriction of opening provided by the forces in the through-thickness direction of the Z toe. So to conclude some of the impact study things that I looked at, we looked at the delamination threshold load, so that it was consistent across architecture and impact energies, indicating that it was a material-dominated phenomenon. We looked at delamination opening and length, and saw that it was reduced in the case of 3D composites compared to 2D. And the mechanisms present that allow that are the Z toe binding and delamination deflection. We looked at post-impact flexural strength and saw that it was higher for 3D composite architectures, and again, we hypothesized that's because the delamination sizes in 3D composites are less than those of 2D composites. So really the big takeaway message as I thought about moving forward in self-healing is that really it's healing of delamination damage that's important. It's this delamination damage that dominates the reductions in post-impact strength after the damage has occurred. So if we're going to use self-healing applications of vascular networks, we really need to target the delamination damage here. So that'll bring me to the self-healing portion of the talk using vascular networks. We looked at two different sample architectures to investigate healing inside of our vascular-reinforced composites. One would be the double cantilever beam specimen, and one is the impact specimen. So if we just generally consider an impacted composite straight away, and think about a vascular network that we might have to incorporate into an impacted composite, you could imagine a vascular network looking something like this, where we have a channel running through, coming up through the composite at one point, and out the other side, where at that discrete point where the channel intersects with damage, we have agents that could fill in the crack point there. But when we consider vascularization of an impact specimen, there's a lot of questions that come to mind that we would like to answer. And those questions can be things like, which healing agents should be used? Should agents be delivered on demand, or should they be preloaded in the channels? If they're delivered on demand, how do we pump them? What scheme is the best? How well do the healing agents mix inside of the sample? Does the network get damaged during impact? Is damage formation different if there are microchannels, and does network incorporation reduce the post-impact strength? So there's a lot of questions here, and thinking about these, they broadly fall into two different categories. And I would call them agent delivery and mixing, so how agents kind of interact in the crack or in the damaged region. And then the impact and the network interaction. And so before diving into an impact specimen and trying to figure out all of these things out sort of at the same time, what we wanted to do is isolate some of the agent delivery and mixing protocols by using a more controlled sample geometry. And the sample geometry we chose to employ is the double cantilever beam specimen. So the double cantilever beam specimen is one where we have a composite beam loaded in mode 1 fracture. So this schematic here is kind of representative of that, where we have a composite beam and a pre-cracked region, and we can load the sample up in these two hinges in tension, and that will force a crack to propagate along the midplane of the specimen to create a delamination damage. So this is a schematic of it, and this is one that I took from Brett Curl's thesis. Jason's work here. This is a double cantilever beam specimen we tested. So why we wanted to do this is that it creates a delamination crack at the midplane of the beam, representative of something that we might see during impact. Then we can incorporate vascular networks into this double cantilever beam to answer those network and healing agent delivery type questions. So the specimen geometry that I'm going to employ during double cantilever beams and what my vascular networks look like to answer these questions is something like this, where we're looking at a top view here and a side view here. So we have 3 microchannels traversing the entire length of the double cantilever beam. And they traverse below the crack plane at one point, and then at roughly 25 millimeters away from the pre-crack, there's a kind of an upswing of this channel through the midplane of the specimen before it then leaves the backside. And so how that looks when we're actually testing the sample and as the crack is propagated is, again, top view, side view. After the crack is propagated through the sample, we actually pierce the microchannel at a location which we know, and which we can call the piercing point. So then we close the sample, and we have a delamination inside of the double cantilever beam, which is sort of representative of what we might have during impact. And we can deliver the healing agents to the backside through those channels in the backside, where we can have our resin and our hardener delivered to the crack plane, where they will then meet each other and mix and polymerize and heal the material. When we first do the opening, we'll have to do virgin testing. And so here we have images from overhead of the crack propagation in the double cantilever beam as it's being tested. So we have low displacement here, and these circle numbers here correspond to the images during the test. And so as the crack propagates from left to right, we have a load up, and we start to see the stick slip behavior of the crack propagation until we get to a point of 50 millimeters of crack opening, and then we unload the sample to close the sample and give ourselves this delamination damage. After this virgin testing, we can evaluate a property of those double cantilever beams during testing known as the critical strain energy release rate. Our G1C is the symbol we're going to use for this, and G1C is calculated as delta U over B delta A, where delta U is the energy required to open the crack, B is the sample width, and delta A is the crack advance during testing. So it's a measure of energy per crack open area. And this energy required to open the crack is simply the area encompassed by this low displacement curve. So for our composites, the G1C value is roughly 975 joules per meter squared. which is on par with fabric and material architectures similar to what I've used. Again, after that first testing, we can then close the sample and deliver our healing agents in through the backside. So the healing agents that we're using here, we're using epoxy resin, Nippon 8132, and an amine-based hardener, Epicure 3046. And these are chosen because they're low viscosity components and they have a lot of heritage in the group, and they polymerize at room temperature, which is important for us. The stoichiometric ratio of these components is 1.9 to 1 by volume, resin to hardener. And to deliver agents through the sample, we're going to use a pulsatile pumping scheme inspired by previous work in the group by Andrew Hamilton. And so in his particular delivery scheme looks something like this, where he's alternating resin and hardener and giving a little bit of wait time between each one of those pulses. So then after we fill all the damage, we allow 48 hours at room temperature, or 30 C, which is sort of the control room temperature, for healing to occur. Then we can, after healing has occurred, reload those samples and get a measure of the healed the healed critical strain energy release rate. Then we can define a healing efficiency metric, which is the ratio of the healed to the virgin critical strain energy release rates. In our particular case, since we have the same sample, which has the same width B, and we're going to the same crack events length delta A, that simplifies to the ratio of the energies required to open the cracks delta U, or the ratio of the encompassed low displacement curves here. So in this particular sample, we had a healing efficiency of 105%. So that tells us that we recovered 105% of the original fracture toughness of the material using our particular delivery scheme.
What is the crack opening of your
So the impact is on the order of 30 to 50 for my specimens. Microns. Yeah. And the DCB, so I do have a binder clip on where the hinges are as it's being healed. And I did put that under the microscope and look at it, and it ranges from about 12 to 30 microns. So we can also look at alternate pumping schemes. So we did deliver in stoichiometric ratios to start, but we looked at also varying the pulse duration. So in this case, we're delivering twice the amount of resin per pulse, or twice the amount of hardener per pulse. And we can also look at delivering in all stoichiometric ratios. So delivering, let's say, twice the stoichiometric amount of hardener, or likewise twice the stoichiometric amount of resin. So we can plot all those results on the same curve to kind of get a feel for how this works. So here we're plotting the percent resin delivered. We're here 65% resin and I guess 35% hardener delivered is the stoichiometric mix ratio by volume. And then we can plot that using the healing efficiency metric, which I described before. And we see that with the longest pulse duration, so 30-second pulse duration, with the stoichiometric mix, we have roughly 95% recovery of these samples. Interestingly, as pulse duration went down, the healing efficiency also went down. So shorter pulses led to less healing efficiency. Also, the system was quite tolerant of excess hardener. And when we had very long pulses and delivered twice the stoichiometric amount of hardener, we had still recovery of roughly 90%, which I thought was quite interesting. However, the system wasn't quite as tolerant as excess resin, and we had roughly 50% healing in the best sort of single heal case with twice the stoichiometric amount of resin delivered.
Question.
Yeah, sure.
The other you go on why you the open is kind of shift in the pulse.
I think it has to do with the coverage of the crack in relationship to where the microchannels penetrate with each pulse. So if the pulse is not able to cover the area which is encompassing the surrounding exit of other microchannels, it might limit the infiltration. I just think it has to do with the size of the area that is filled during each one of the pumping pulses.
Kevin, certainly the healing efficiency 30 as well as second pulses are not significantly different.
Sure.
Is there any additional evidence that you reach the maximum beyond that, or is that not enough?
I would have to go back and look at it. I can't sort of remember off the top of my head, but certainly images of the crack line after this sort of
How lower percent resin they are significantly different, so there might be a little more.
right. So we can take the best performing healing cycle from our single heal tests and actually apply that over multiple healing cycles. And if we use multiple healing cycles, we have to be sure to keep the channels clear during each one of these cycles. And so when I'm doing these multiple healing cycles now, we're actually purging the channels during the healing event between each one of these cycles. So that's one distinct difference between the two different methods. So when we do actually apply the best healing agent delivery, we do see repeat healing is possible as long as the channels are clear, and we're able to show up to 10 cycles of healing with roughly between 50 and 65% efficiency. And this really is the first demonstration of 10 multiple healing cycles, taking advantage of the vascular redelivery over and over to the same area of the crack plane inside of the specimen. So I thought this was, I think, one of the better accomplishments of my time here at Illinois. So to continue with my outline, sure. So we think that it has to do with the purging of the channels, sort of led to air, which also may have purged some of the healing agents around where the healing agents were pushed into the crack plane. So I think just the fact that we ejected some healing agents not only out of the channels but out of the crack plane as well led to reason for that. We did look at Raman microscopy of the cross-section, and we looked at what was the mix ratio at discrete points in the cross-section. And we did see that the mixing ratio of the components near where the channels were located was lower than the mixing performance far from the channels. And so there may be healing agent injection, or there may just be worse mixing near the site of egress from the channels. There could be a lot of things that cause reduction. We did look at both. Yeah. It occurs in both. Yes. Yeah, I mean, it did come out of the size a little bit of the sample as I did the healing.
Can you explain a little bit, because this is one area that I was... Okay, I can see the first crack having to do, and then you get the healing agent, then it heals, then you do it again.
Right, so
How does the things are not blocked now, right, the channel, right? So does the crack go to the same position, differently, maybe cut the channel, but the other one is blocked now? So now you're saying you flow air, and then the healing agent goes out?
right, so
That holds at that point there, or what, right?
So yeah, sorry if this was unclear, but when we bring the sample back together the first time and heal it the first time, the air purge is done immediately after we deliver the healing agents. So the channels are kept clear by keeping the air pressure on the channels throughout the duration of the healing cycle. So that's what keeps them clear. And so the healing agents are in liquid form immediately when we deliver the air, so that's how they can migrate into this multiple healing agent.
Okay. So the healing agent that you're saying is coming out is because of this air escaping while the healing agent is still in the liquid form, which makes it little.
Yeah.
Therefore,
This red line here is 2, this is 7. So it's been healed 2 times.
Okay.
ones that are not shown here, right? So only the black one shows kind of the
Yeah,
stage.
the black one is the virgin phase.
Right, so only down to the because this, this main cycle is just.
Well, yeah, I mean, those were done, I just the graph of the comes from all those.
Right. So, but none of them show this.
Yeah, it looks like more of a very dynamic propagation. Maybe this one had a little more ductility or slow opening, but less kick slip.
The rest is pretty far out.
Right. So on the back end, far from the channel on the back side. So it's hard to really quantify it using this. You have to plot it as G1C as a function of delta A. Would be more useful, so I can't say straight away. I would guess that it probably dynamically propagates near where the channels are. Oh, I would say somewhere in the middle of the propagation, maybe here or here. Yeah. Okay, so I'll continue now with looking at impact specimens. So at the same time as I was kind of going through the double cantilever beam specimen studies, there's another graduate student named Brett Kroll who was looking at a new sort of delivery method which overcame some of the mixing problems that I saw sort of in the ECVs and that previous researchers before me had seen with these two-part healing agent systems. And he used a new sort of way to deliver agents to the crack plane, which he coined air-assisted reagent propulsion, or ARP for short. So he was in this particular system. What he did is he had a central channel which had high pressure air flowing through it and high velocity air flowing through it. And tangent to those, we had our liquid agents, the epoxy and the hardener, coming into the side and streaming into this main air line. And so the air that's moving at high velocity would actually shear these droplets off into the airstream and then deliver them to the crack plane as discrete droplets instead of as a continuous stream like what I had previously done with my double cantilever beams. And he was able to show significant improvements in the mixing using this. So this is an image from his work overhead. Again, our air is flowing from left to right here, and our epoxies are coming from the bottom. He used aziol as one of his healing agents. And so we see the formation of discrete droplets traveling along the length of the air channel as they're getting delivered to the site of damage. So I wanted to take advantage of this in the impact specimens as I move forward. And so to design our healing of our impact specimens, we used, again, our beam specimens, which is the same as what we did in the first part of the study, looking at damage characterization. We're using the same materials, so again, S2 glass plane weave, H62000 resin, using a vacuum-assisted resin transfer molding technique for infiltration, same cure schedule. And now we're adding an evacuation step. So sacrificial component evacuation, 24 hours at 200 C. So again, we're incorporating these sacrificial elements and then evacuating them afterwards. And so the network geometry here is two channels with piercing points in two separate locations. And then we have external to that our air-assisted reagent propulsion mixing chip. And this is also made out of composite in a similar way with sacrificial components evacuated out afterwards. And the reason we made this external is so that we could have consistency between our different samples, and also so we could quickly deliver to multiple different channels in sort of a sequential pattern. So the impact testing procedure is very similar to what we did before, using the same impact setup, so 25.4 millimeter radius of curvature, 4 millimeters of free span, and then impact energies range from 0 to 15 joules in this particular case. So to deliver the healing agents, we had a setup that looked something like this. We had resonant hardener components sort of stored in syringes and delivered using a volumetric delivery through a syringe pump to our mixing chip. The air was controlled on the backside by holding the pressure of the air constant during the entire delivery. Then we had a small amount of Pygon tubing going between the mixing chip and the Fletcher sample. And we monitored the filling of the Fletcher sample overhead using a camera. This was all synced together using a computer that might not be that archaic, but a computer. The healing agent delivery setup, again, if you want to visualize this, looks something like this. Here's our mixing chip with the resin and the hardener components going into the opposite sides. And we have the air coming in on the backside, which is pushing those components. And then it's delivered through the short amount of Pygon tubing to our Fletcher specimen that's been impacted, which you can see here. And so this is sort of the damaged region. You can see the optimal mismatch which occurs in the alienation. So these are some images of the filling occurring from overhead. So we can fill the channel sequentially. So we first fill channel number 1, then channel number 2. So channel number 1 is going to start by infiltrating the channel from below, and then it actually pierces through the delamination at this point here. So we can start to see some index matching occurring over time with this particular impact specimen until we're finished with that channel and we stop seeing more infiltration of damage. Then you can imagine this sample is flipped 180 degrees, and now we're coming in on the opposite channel. Again, the piercing point is roughly in this location, where it goes down to the sample, and then we start to see increased optical matching, indicating that we filled some of the damaged regions. What's interesting to note is that even in these particular situations, not all of the damage is filled. We think that this has something to do with the damaged connectivity in the material, and I'll discuss a little bit more about that when we get to some of the cross sections of the material. So then we allow. Oh, sorry. These are 20 millimeter width specimens, and then this damage region is roughly 40 millimeters, which is unclosed standard impact.
So where are the plants?
So there's no clamps in this image because this is of the damage filling. So in the impact, the clamps would stop roughly here. So it's fully encompassing the damage. So after allowing 48 hours at 30 degrees Celsius for the healing to take place, we test these samples in post-impact pressure again. So our outer span is 80 millimeters, inner span 40 millimeters. Again, we're looking at flexural strength and secant flexural moduli. But now we can define two metrics of healing efficiency for both the strength and the moduli, in which we have the healed minus the damaged flexural strength divided by the undamaged minus the damaged strength. So it's similar to healing efficiencies previously observed. Similar with the moduli, healed minus damaged over undamaged minus damaged. So if we plot the flexure testing results here, we're plotting the strength and stiffness for moduli with the different impact energies. We see with no damage, we have a nominal flexural strength of about 520 megapascals. When we introduce damage, we have a reduction to about 220 megapascals with 10 joules of energy. And when we fill impacted specimens and allow them to heal, we have recovery of about 37% of the healing efficiency. Similarly, if we look at the reduction for 15 joules, it goes down to approximately 180 megapascals. And then when we fill the systems that allow them to heal, we have a recovery from that damaged state of 47%. Similarly, with the flexural moduli, we see recovery values of about 80% and 83% for 10 and 15 cases. So this was the first demonstration of restoration of mechanical properties in an impact specimen using vascular delivery of segregated epoxy and components. And so this was another, I think, nice accomplishment of what I've done here. We can take a look at cross sections of samples that have been impacted and filled with our healing agents. We can take a look for visual evidence of healed material inside of the crack. So we have the healed delamination here, healed delamination here. And interestingly, like I mentioned before, there are still regions that are unhealed. So we have this delamination here, which did not receive healing agent and was not healed. And we think that this has to do with some of the damage connectivity issues, and that we have a segregated area of damage which does not have a connection with the microvascular network to receive healing agents. We cannot heal those damaged regions. We can visually kind of quantify the amount of damage fill using what we call filling efficiency. This is sort of an optical technique using the images from the filling of the samples during the healing process. So if we compare undamaged, damaged, and healed specimens, convert them to grayscale as shown here, and look at the average pixel intensities of each one of these images, we can come up with a value of average pixel intensity for each one of these. Then come up with a metric of fill efficiency, which is simply ratios of these particular agents, which measures on a scale of 0 to 1 how much damage has been filled based on this optical technique. What we do then is we can plot the healing efficiency as a function of the filling efficiency, and there's kind of two things that you'll notice here. One is that the healing efficiency tends to positively correlate with the filling efficiency, and also we notice that the fill efficiency values tend to be higher for samples that were impacted at 15 joules compared to samples that were impacted at 10 joules. And we believe this again has to do with damage connectivity. Samples that are impacted with 15 joules are more likely to have more connected damage than those impacted with 10 joules. So to conclude some of the impact studies, we demonstrated self-healing of impact damage in vascular fiber-reinforced composites. We had an average of about 47% of the post-impact flexural strength recovered, and about 83% of the post-impact modules which recovered on average. We also saw that the filling efficiency correlated with the recovery of post-impact strength, indicating that the more that we were able to fill, the better we could do. Okay, so I'll finish off now with some of the grand conclusions of my work, a summary of my accomplishments, and some analogies. So to conclude briefly, we looked at delamination damage which occurs during impact, and we saw that it led to lower post-impact strengths. We saw that 2D composites tend to have larger delaminations and lower post-impact flexural strengths than 3D composites, and we believe this as a result of the larger damage. We demonstrated delamination damage being healed using pressurized delivery of epoxy-amine healing agents, and we saw up to 95% efficiency, slightly lower efficiency for multiple cycles, but up to 10 healing cycles per positive. Also, looking at the cross-sections, we were able to visually see that impact damage was healed using this novel air-assisted reagent delivery technique. In an average of 47% of the strength and 83% of the modules was healed in the 15 locations. So to highlight the contributions of my time here at Illinois, when all is said and done, I'll have 5 publications. If the boss is okay. Okay, them. And I'll just highlight in red here kind of the contributions of each one of these papers. Quantification and comparison of impact damage formation in 2D and 3D woven composites. Quantification and comparison of post-impact mechanical properties. So this is sort of a part 1, part 2 set of papers. Then we have a paper on the first demonstration of in-situ healing of delamination damage over 10 healing cycles using vascular delivery of agents. So this is the double cantilever beamwork. Then we looked at the first demonstration of self-healing of impact damage in a vascular composite by delivery of segregated epoxy-amine agents. Finally, one thing I didn't really talk about today was looking at alternate chemistries for providing some of this vascular healing. And we did successfully create a novel cross-linked epoxy for some latent self-healing applications using an embedded imidazole functionality. I contributed to 3 other papers as a co-author, one with Brett Curl and Jason Patrick, looking at a novel method for automatically tracking track propagation during double cantilever beam specimen testing. One I co-authored with Jason Patrick in Advanced Materials, which was the first demonstration of in-situ healing of delamination damage using vascular delivery of agents. And then I was also part of a review article on self-healing materials in 2013. I was also part of one patent here with Jason kind of as the name here on self-healing composite materials and microvascular composites for forming the materials. Lawyer speak, I guess, there. And so now we get to the acknowledgement slide. And I mean, I said for a long time and debated how to do this because there are so many people that contributed to this work, and I'm so thankful that have been a part of all of your lives during my time here. Undergraduate research assistants, Ariel, Ryan, Patrick, Larry, Seth, Isaac, very good for doing tedious things I didn't want to do. And you can talk to Ryan Merriman after this if you want to hear more about that. The U.S. Army Research Laboratory funded me for a majority of my PhD, and I had some great advising from Dr. Garrett Wetzel out at the Army Research Lab, who I will subsequently work for here in a couple of months. The committee members, obviously, Professor Soda, Professor Cabell, Professor Weinrose, for sitting here and listening to me ramble for the last hour. Especially Professor Sotos. I've learned so many things from you, how to improve your technique, how to put together good presentations, scale bars. I mean, you've been a great advisor to me. Everyone in this room can attest to that. AMS members, obviously, you guys have made my experience incredibly enjoyable, not just for scientific contributions, but for other fun reasons as well. And I'll give a special shout out to, Dr. Tony Coppola now, Dr. Jason Patrick, and Stephen Petty, sort of my collaborators in the composites world. I also want to thank the people at the Aerospace Machine Shop, Greg Milner, Stephen Dean, and Boer. They did a lot of sample fabrication for me, so that was nice. All of my friends and family, it's amazing to have all of you guys here today. I appreciate that. And there are 2 people in specific which I want to give a special thanks to. And number 1 is my dad. So you've been there for me financially and emotionally through this time. So thank you for that. And boss man, I've learned so many things from you. not just how to be a good scientist, but how to be a good person. So, thank you. That'll do it for me. Thank you. Okay, questions?
What are you wearing in that?
That's pointing the line I read.
What are you wearing?
Those are my dreads. They only come out on special occasions.
All right, so the floor is open for questions.
Yeah, Brett?
Yes, first of all, really good talk, really nice science. You mentioned that in the vascular samples, higher impact energy, you get better flow.
Yeah.
Does that translate to better healing with a higher impact energy, or is
Right,
the
so-
impact energy going to cause so much damage that you're going to?
Right, I think there's competing factors there. That's definitely something we have to consider. I mean, you did see that we did have better healing efficiency in the 15 joule case, but the nominal strengths of the healed samples in both the 10 and the 15 joule cases were approximately the same. So if you want to quantify healing as the delta between the two, then yes, we did have higher healing efficiencies with higher fill efficiency. But if you want to use an absolute metric for the residual strength, then yes, it's a competition between the damage you impart and healing you get.
Piggyback on the press question, I thought it was fascinating because it was implied that you need less plumbing to fix more damage.
Yes.
Right. Inverse of what you might guess, but when you see how it is.
So if we have extreme damage, only one channel.
Did you ever explore any different sizes of the Z-drops?
No, we only use one particular fabric for this study, but I think that would be interesting to look at. Yeah, Paul.
Do you lose anything in terms of material capability when you put the capillaries into the composite for the self-healing? It seems like you'd be taking away some
Yes.
sort of strength from that.
I think has some data to back that up. So this is a comparison of unvascularized versus vascularized samples of different impact energies. So here we're plotting the strength as a function of impact energy and the Fletcher modulus. And so in the nominal case, not a significant amount, but with the introduction of impact damage, actually having the vasculature in there sort of reduces the strength substantially.
Is that a fatigue at all, or having that capillary almost kind of act as a little starter crack in there under fatigue?
It could act as a starter crack, but it could also act as an arresting, as a way to arrest the fatigue crack. And there was work previously in a group where Andrew Hamilton, someone from our group before, looked at how the microchannels actually increase the number of cycles to failure in fatigue by actually arresting a fatigue crack. Questions?
I have one. You emphasized in the presentation the importance of the connectivity damage, right? Because indeed there was some that were not reached because they were just not connected to the damage that was caused in microchannel.
Sure.
So you mentioned, yeah, if there's extensive damage, maybe they're all connected and therefore you can heat them all, right? That's what you mentioned. But so for intermediate type of damage, what would be the optimal? If you had to re-optimize these, how would you distribute these type of channels, right? I mean, you had in one example that I showed, you had two microchannels that were intersecting the fracture plane location. How would you do this?
Yeah, I mean, for demonstration purposes, what I did, you could argue is rather arbitrary, right? So what I did, I mean, I did pick locations where I thought the vasculature would penetrate and intersect at elimination, but I mean, your question is a good one, right? Like, how would you design the network if you're not really sure exactly where the damage is gonna hit, and what density do you need to ensure that the damage does intersect the channel? I don't know the answer to that, but you know, I think with increasing or decreasing impact energy, the density of channels required would go up or down, kind of like what I think what Rob alluded to. Yeah, I think it is an interesting question, and I wouldn't be able to answer it straight away.
Given that in the original motivation, the microcapillary system work pretty well for small damage, to combine the two together, because the more
Yeah.
damage you put in, the worse it becomes.
Right.
Just to give the strength to get the shape on the rest.
Sure. Sure.
You only need them when the damage is big, the other ones are.
Right. Yeah, I have considered it. One particular issue is capsule stability at high temperature. So we require 200 degrees Celsius for 24 hours to complete the vascularization process, and the capsules don't survive that typically. There has been a paper published recently by someone at the Urbana-Champaign that looked at adding a different polymer coating to the outside of the capsule, as a polydopamine coating, to increase the thermal stability of the capsule up to 180. And then Amanda Jones capitalized on that in one of her papers. So I think this technology has come along, and it could be something that's viable. And actually, in the conclusion to my dissertation, I make note of that. So, yeah, it's really interesting.
The way that you laid out the presentation was chronological. So, you know, it's right now, delivery of healing aids, protocol, policy, the DCD is a lot of systems. Then what the impact could be different in delivery. So
Right.
what happens when you use that pumping protocol?
It doesn't work very well. Yeah, you know that. Well, that's a question I can't answer. I should have included it.
You also did a lot of work on the digital system. Did you ever? Did he use the same digital
I did actually venture into creating composites and actually showing, using some sort of reference test that we could heal some small amounts of impact damage using sort of a vacuum infiltration of epoxy agents and then healing the composite at high temperature. And I do include that in the appendix of my dissertation, but only that slight demonstration was ever really pursued. But I think, you know, that's something that I included in the future work of my dissertation is I think it could be a really useful healing technique moving forward. I just didn't pursue it.
Could you comment on how you choose your healing agents? So you commented a lot on increasing healing by changing the mixing and the pumping protocols. But what about changing your healing agent? Maybe one with a higher G1C. I don't know how you would do that. So.
Yeah, I selected my healing agents for many reasons. Heritage, their low viscosity, kind of well understood in the group. I don't know if I can comment much on how it would change with other healing agents because I didn't explore many other agents. Brett Kroll did some work with thiol-based hardeners and epoxies, but the way that he delivered them was significantly different from the way that I did. So it's hard for me to make real direct comparisons. I just haven't picked what I knew a lot about and went with it.
Seems like a natural point here. To kind of take a short break, the committee is going to go into one of those more depth where you're welcome to say what. I said,